Today's lesson is going to revolve around the concept of rational functions, specifically answering the essential question, how do you solve rational equations? Rational equations have the form f of x divided by g of x equals 0, but can be written in other fractional forms as well. In the form that's given, it's one function f of x divided by a second function g of x equal to 0, but other forms might involve the addition or subtraction of rational expressions, not necessarily even equal to 0. But if you can write the function in the form f of x divided by g of x equals 0, then we can use cross multiplication to solve, as we've seen before in solving for x-intercepts. If we cross multiply and multiply f of x times 1 and g of x times 0, to solve the fraction f of x over g of x equal to 0 is essentially the same as solving f of x is equal to 0. So when we go to solve rational equations, if we can get our expression in the form of one fraction equal to 0, then we can solve for the numerator equal to 0. With one possible exception we'll see in a little bit. So here's an example. We'll solve algebraically first, and then we'll confirm our solution numerically. Something we used to do a lot in elementary and middle school whenever we start solving equations in middle school, checking our answers. So here's a situation where we've got a fraction equal to 0. Remember, we solved this as a proportion, and essentially by doing 3x minus 2, your numerator, equal to 0, and solving for x is equal to 2/3 is our solution. If we check that by plugging in into our original expression, 3 times the quantity 2/3 minus 2 divided by 2/3 squared minus 9, we want to check, does that actually end up equaling 0? So our numerator, we end up, the 3's cancel, and we end up having 2 minus 2 in the numerator. In our denominator we have 4/9. 4/9 minus 9. 9 is 81/9, so 4/9 minus 81/9. Does this equal 0? So 2 minus 2 is 0 in our numerator. 4/9 minus 81/9 is a negative 77/9. And 0 divided by negative 77/9 is 0. 0 does equal 0, so we've checked our solution. Okay, here's an example where we don't have just one function equal to 0. We actually have the difference of two rational expressions. So we know what to do. We need to get common denominators and combine the two expressions. So our least common denominator is going to be the product of the one denominator 9 and the other. So x over 9, we need to multiply times x over x in order to convert that into having the common denominator. So x squared over 9x. 1 over x we need to multiply by 9 over 9 to get our common denominator. We end up with 9 over 9x. So our original expression x over 9 is now x squared over 9x. Minus 1 over x is now 9 over 9x. Equals 0. We can now combine these two to get x squared minus 9 over 9x equals 0. From this situation, now we're ready to solve our numerator, to cross multiply and solve our numerator equal to 0. So x squared minus 9 equals 0. X squared equals 9. We're going to square root, and when we put the square root into the problem to solve, we're going to remember that our solution is both positive and negative 3. Okay, so here's our answer, both positive and negative 3. We've got to check them both. So when we go back to plug in to check our solutions, we've got to check them both. So let's check 3. So 3 over 9 minus 1 over 3. Is this equal to 0? 3 over 9 is 1/3. 1/3 minus 1/3, that is definitely going to equal 0. So good. So 3 is definitely solution. Let's check negative 3. So negative 3 over 9 minus 1 over negative 3 equal to 0. Negative 3 over 9 is negative 1/3. The minus the negative here actually turns into plus a positive, so this is plus 1/3, and negative 1/3 plus 1/3, 0 equals 0. Good. So both 3 and negative 3 are solutions. If it seems a little strange why we are checking our solution, we'll see here in just a second that that's actually going to reveal one little trick to these problems that we can't ignore, and we're going to want to take note of right from the beginning once we see it. So okay, here's a third example. Notice the 1 here on the right side of the equation. So I'm going to actually start out by getting the entire getting the right side equal to 0. So I'm actually going to subtract the 1 over to the other side, so we have equal to 0. Now our least common denominator is the product of 3 times x plus 4 is our least common denominator. So we're going to convert each of our rational expressions, x plus 1 over 3, that needs to be multiplied by x plus 4, top and bottom. Do a little better. X plus 4, top and bottom. And when we do that, we're going to actually FOIL our numerator and get x squared plus 5x plus 4, but we keep the denominator factored, remember, 3 times x plus 4. Okay, 9 over x plus 4, that needs the factor of 3, so we're going to multiply by 3 over 3, and that's going to get us 27 over our common denominator. And then 1, of course, is the least common denominator divided by itself. That's since the value of that is just 1. So now our new expression, our x plus 1 over 3, is now x squared plus 5x plus 4 over the least common denominator. We're going to subtract 27 over the least common denominator, and we're going to subtract the least common denominator, which I've FOILed out here, over the least common denominator. And all of that equals 0. So we're going to combine like terms. There's only one quadratic term, so that's going to be x squared. I'll write it over here where I have more room. We've got one quadratic term, x squared. Here's a 5x, and here's a negative 3x. So those are our linear terms. 5x minus 3x is 2x. And then our constant terms, we've got a positive 4, we've got a negative 27. And be careful here, this negative or this minus needs to be distributed to the 12. So it's actually a positive 4 minus 27 minus 12, which we end up with a negative 35. Negative 35. And all of that is still over the common denominator. and now we have this written as 1 fraction equal to 0. 1 fraction equals 0. So we can solve our numerator, x squared plus 2x minus 35 equal to 0. That factors into x plus 7, x minus 5 equal to 0. Our solutions are -7 and +5. Okay, -7 and +5. If we check our work, we've got to check again the -7 and the +5. So -7 plus 1 is -6/3. We're going to subtract 9 over -3, and we want to know, does that equal 1? So -6/3 is -2. The negative minus a negative is a +3, and does that equal 1? And 1 does equal 1. Good. So the -7 checks out. Let's try the 5. 5 plus 1 is 6/3. And then minus 9 divided by 5 plus 4 is 9. Does this equal 1? 6/3 is 2. 9/9 is 1. 2 minus 1 is 1. So yes, both of these are solutions. So that last example that I had mentioned before looks like this. So let's go through the steps and look at what needs to happen. As I did before, I'm going to subtract the term on the right side over to the left side so that we get the right side equal to 0. Now we're looking for our least common denominator, which in this example, 2 of the rational expressions already have the common denominator, x minus 1, which means we really only need to convert the fraction x over 1 to have the common denominator. So that needs to be multiplied by x minus 1 over x minus 1. Okay, distributing up top, we have x squared minus x divided by the common denominator. So our original expression looks like x squared minus x over the common denominator plus 5x over the common denominator minus 5 over the common denominator, all equals 0. When we combine like terms, this simplifies into x squared plus 4x. Here are your linear terms. This is a -x and a +5x. Combined to get us a +4x, and then we have the minus 5, all divided by the common denominator equal to 0. Okay, so here's this 1 fraction equal to 0, and the way we've been solving this is by taking the numerator, x squared plus 4x minus 5 equal to 0. Solving that, we can factor that numerator equal to 0 and solve to get x equals -5 and +1. Okay, so this is the answer that we have been that we would get by doing it the way that we've been doing. But when we check our solution, when you plug in -5 for x, -5 plus -25 over -6, we want to know, does that equal 5 over -6? So we need to convert -5 here to the common denominator of which is 6, so this is -36. The -25 here divided by -6 turns into, 2 negatives turn into a positive, so that turns into plus 25/6. We want to know, does that equal, we'll move the negative out front, -5/6. And -5/6 equals -5/6. Okay, -5 is definitely a correct answer. But what about this 1? Let's check. 1 plus 5 over 0, equals, we're not sure, 5 over 0. Now, from all the examples we've done in class so far this year, we've always tried to avoid 0 in the denominator because it's an undefined expression, and this is no different. The fact that this and this are undefined expressions means we can't proceed in checking 1 as a solution. And in fact, 1 is not a solution. 1 is not a solution. What we say is we call it an extraneous solution. It appears to be a solution, but it makes the original expression undefined and therefore is not a solution at all. And what we could have seen during the problem when we got it to the point of combining to have one fraction equal to 0, when we got to this point, we solved the numerator equal to 0. An alternative approach is if we had kept the numerator but factored it in the context of the rational expression, you see that the common factor x minus 1 on top and x minus 1 on the bottom cancel out. This canceling makes the x minus 1 an extraneous solution. And in fact, we don't even mention it. We don't even talk about the extraneous solution. We don't need to. We just ignore it. We can check our answer and assume that it's extraneous. Well, once we check our answer, we know that it's extraneous, and then we forget about it. It's not an actual solution. And with this reducing of common factors, we're left with just x plus 5 equals 0, and that's going to leave us the only legitimate solution, the only actual solution. So when you're solving rational equations, checking the extraneous solution is essential.